Now let's do a numerical example to see how these formulas apply. So an example. So let's say I have two plates. Here's one plate and there is another plate underneath it. Draw it with a different color. And there is a hole through this plate and there is another hole through the top plate. And through these two holes goes a bolt. So there is a bolt that goes through these two holes and there is a nut. All right. And you're going to basically tighten this nut. So about this axis, you're going to rotate the nut, and as a result, this bolt will tighten, will keep the two plates compressed. So let me bring the bolt down. So we are here, and here is my bolt head now. All right. Now, when I do this, I essentially put my bolt in some sort of tension, right? So if I look at the free body diagram of the bolt alone, what do I have? So free body diagram of the bolt. I'll draw it a little bit bigger. So here's my bolt. And because I've tightened my nut, the bolt is in tension with some force T. Let's say this tension T is given to you as, I'm just going to make this up as 50 Newton, okay? All right, so I've got this 50 Newton force of tension. Now the question is, what is the stress, normal stress in, let's say, this part? So if you make a cut over here, then what is the normal stress at a cross section over here, which could be same as here or could be same as here, because there's really no difference in these three planes. And what is the strain that develops as a result of applying this tensile load? And what is the elongation in the bolt, and what is the contraction of the bolt in the transverse direction? So there are all these questions that we are trying to answer. Okay, so first of all, we have to understand that if we are applying this tension T of 15 Newton at the two ends, the stress that develops in this area may not necessarily be the stress in this area. Why is that? Well, first let's look at what happens in this area right over here. Okay, so let's say the diameter of this bolt is given to you as, let's make it up as 5 millimeter. Then the cross-sectional area is pi d square over 4. So that's 3.14 times 5 millimeter in meters would be 5 into 10 power minus 3 square divided by 4. So let me plug in these numbers in my calculator and see what I get. So I will have 0.005 times 0.005 times 3.14 divided by 4, and that gives me area as 1.96 into 10 power minus 5 meters square. So that's the area. So what is my normal stress in that cross section? It will be the force tension divided by the area. Tension is 50 Newton divided by 1.96 into 10 power minus 5. So this will be Newton per meter square, which is equal to what? So let me compute that. I got into 50. So I got 25.5 into 10 power 5 Newton per meter square. So that I can write as what? I can write that as 2.55 into 10 power 6 Newton per meter square. And I'll tell you in a minute why I'm doing it this way. Okay. So this is basically 2.55. 10 power 6 is actually mega. So I will write it as M. And Newton per meter square is same as Pascal, so I'll write it as Pascal, so megapascal. So sigma is equal to 2.55 megapascal. And typically you will see stresses being reported in terms of mega or gigapascal only. So that's the reason why I want to bring that factor of 10 power 6 over here. Okay. All right. So that's good. Now let's compute the strain. So strain is defined as delta L over L. Okay, and now remember, we're doing all this calculation only for the tensile loading. Different kinds of loading will give rise to different kinds of stresses. So we'll talk about another kind of stress pretty soon. So for this, we have to know what the original length was. So let's say the original length is given to you as 5 centimeters. Okay, so that we have the original length. Now we need to find out what delta L over here is, right? Because from this equation alone, we cannot find what the elongation is just knowing the length. We also need to know the strain. So either we need to know the strain so we can compute the elongation, or we need to know the delta L so that we can compute the strain. So let's say we are also given delta L to be, I don't know, we'll call it maybe 1 millimeter. So delta L is given as 1 millimeter. So this would be 1 into 10 power minus 3 meters divided by original L is 5 centimeters. So that will be 5 into 10 power minus 2 divided by the meter. So you can clearly see that epsilon is actually a dimensionless quantity because the units actually cancel. So we get what? We get 0.5, no, not 0.5, actually 0.2. We get 0.2, that's 1 over 5 into 10 power minus 1. So that's actually 0.02. And that's a dimensionless quantity. Now, typically the strain will not be given as 0.02. We will most of the time report it as a percentage, so it will be actually 2%. So we'll say it's 2%. So if the strain is given as 2%, we know actual strain is 0.02. Okay, so that gives us the strain. Now, our third question was, what is delta D, right? What is the contraction? That's the other thing. So for that, we need to be given the Poisson ratio. So let's say Poisson ratio is given as 0.3. And that is equal to minus delta D over D in the numerator divided by delta L over L. Okay, so do we know everything here? Looks like we know the D, we know delta L over L, which is actually our strain. So we can compute that. So delta D over D, I'll bring this on one side, is equal to minus 0.3 times this quantity here is nothing but the epsilon, right? The strain. So that's 0.3 times epsilon. So that's minus 0.3 into epsilon is 0.02. So that's what, that's actually 6 into 10 power minus 3 negative, and this delta D over D. So delta D is equal to minus 6 into 10 power minus 3 times the D, and the D is 5 millimeters. So that's 5 into 10 power minus 3 meters. So that gives us what? Minus 30 into 10 power minus 6 meters, which in terms of millimeter, if you want to report it that way, it will be minus 30 into 10 power minus 3 millimeter, and I would bring this 10 power minus 3 on the other side, so it will become minus 0.03 millimeter. And the negative sign over here indicates that it is actually a contraction because there's a reduction. Now let's say we want to answer a fourth question. Under this tensile load, is this bolt going to fail or not? Okay, so failure could be that there's too much tension applied, and it could fracture, or it could elongate to the extent that it no longer serves its purpose in some way. Okay, so that question cannot be answered at this point, because to be able to answer that question, we have to know something about the property of the material. Okay, and that's something that we'll discuss in probably the next video.